It's another brief moment in time. We get to see the change on the timelines. We're shifting, twisted bits of technology, something lifting up the little bits of reality. While the train drifts through the space-time, we're surely a randomly sparking the photons around me. Let the light flow from the heat show when the photons ignite, highlight in yo. Then you'll know it's that time when we force a change in our mind's eye. Ho ho! A little bit Linux with something in us. It's almost like we something else, autonomous, or maybe perhaps it's that missing piece you need. Perhaps it's that simple message you're searching. Perhaps it's just a different time framing. Us people match the fake shoe in the mainframe. Getting excited, so are the photons. Don't laminate so we can change the coupon. Let me raise the hash rate, so make the coupon fake. It reflects the rate while I major bags. Crypto technology, like cryptographic money and hashing your life into a set of QRs. It doesn't matter, cause this was 3D change perspective. Welcome to the show. Welcome to the show. Welcome to the show.
What up, everybody, and welcome to the show. If you guys would just give me a quick second while I get everything going and doing as we normally do. Because yes, I am meaning that today we're going to basically talk about connecting databases, communicating them together like blockchains, specifically blockchains, but we're going to start with databases and work our way up to it. Because how we communicate with databases does change or advance. It's just basically like it doesn't stay the same, so it has to change and advance, and we're going to talk about why or how that change and advancement plays out, because it's not as cut forward as most people would assume. Okay, why can't I get the YouTube part thingy right there? That thingy. Find it. Still not. Hold on, everybody. I'm having a hard time actually getting the thing to bring up the thing I'm looking for. I apologize for the inconvenience. That's not sure. Okay. We're just gonna have to go with it. So, what I want to go over the different solutions connecting these databases like the blockchains to each other, especially when neither database knows of the other, because that's an important difference that a lot of people don't realize. When you're talking about interconnecting blockchains together to do something, knowing that the other one exists is kind of important in order to actually get something done, to actually do something that is, you know, what we would call interconnected, or you know, where it's not just seemingly, where it really is actually interconnected. Okay, so I want to thank today's sponsor while we keep going forward, because we are using a brand new browser. I'm testing something out for a future episode. I'm already having problems, and I do apologize. But as you can see, my character model is running a little bit better than usual, which means the one I'm running is a more lightweight, more lightweight setup. I just have to figure out how to get all of it to properly work together. And that is where we're going to be having problems today. So I do apologize for any hiccups you might be seeing going forward. Now again, I want to thank today's sponsors and partnerships, because we do have the Deorganized partnership up with Team Bitcoin Live Digital Broadcasting DB, because Bitcoin Live DB and Deorganized is a powerhouse combo. And I see new heights for both organizations. And if you haven't checked out Deorganized, their early morning broadcasts for stacks and other topics seem to be taking off. The more they go on every day, find them on Twitter and among other social platforms. I also do want to thank today's sponsor, and it is a great sponsor. It's the same sponsor I've had so far. I want to thank Shieldfolio for sponsoring today's episode and BitcoinLivejn. Because without Shieldfolio sponsoring today's episode, we wouldn't be able to do this from within the quantum pit. And if you haven't seen a Shieldfolio wheel, it's like a little black book that are made from stone paper. So they're fade resistant, dirt resistant, even water resistant. So you know the info and secrets you store in Shieldfolio will last and survive whatever you throw at it. I personally have a Shieldfolio and use it for my website info, contacts, with the keys, among other things. So it's the little black books that are pocket sized and ready to be by your side regardless of your adventure in real life or online. And I absolutely really do love them. Now, if you see at any point in time during today's episode, there's a little QR on the bottom middle screen with the Shieldfolio shield. You can scan that and it will take you to their website. But if you look in the middle of the screen, we also have that same QR up bigger for you. So you can go ahead and scan it and use BitcoinLive20 when checking out today to get 20% off your order today. Awesome sauce. Thank you again, Shieldfolio. Let's roll in with the roll-ins and see how this goes. Thank you again, Shieldfolio, for sponsoring today's episode and BitcoinLivejn. Alright, so right now you could be watching this across multiple different platforms, multiple different areas, and if you are on X, Twitter, or YouTube, there's a chance that your chat might appear on the screen. I have been working hard to try to get this to work again, so hopefully it will work. The only one I don't see actually popping. Let's see what happens. Oh no, there it is. Okay, so alright, I got them both up and ready to vibe. So sweet. And doing another test on X Twitter. So if you're on X Twitter and you see us, say hello, see what happens. Because today we are, well, in the greater fourth dimension of the quantum machine, and we want to walk you through how we're going to do today's episode. Like every episode, we are going to display a QR on the top of the screen. So at any point in time you are watching, if you see a QR on the top right, or answer top right, yeah, it should be like right over there. If you're seeing that over there, then you should be able to scan it and follow along throughout the entire episode. So that way you don't ever have to worry about anything. That means if you're watching this live or you're coming back watching it later or anything like that, we have you ready to go. And for example, like right here, I want to point out this is the Organized Media, who I mentioned earlier, and you saw it pop up a little bit. They go live almost every morning and every evening, so check them out for your daily hookup on what's digitally popping. As you see, I have their live here, and they are very vibrantly hard working, doing their thing. So before we get into today's topic, I do want to give you guys a free pre-search query. This is something we've been doing this year, and it's just another way that you can get more information on today's topic that isn't going to be directly, I didn't actually go through this and use any of this directly, so if it does appear, it's by accident. So this is just another viewpoint that you can get later on when you want to look more into this. And today's query is blockchain database connections. So today's free pre-search query again is blockchain database connections. This is an image query. I haven't done this yet for you guys. So this should specifically find you images to help explain a bit more of how blockchain database has connections and connects. Because we're going to get into it. It gets kind of tricky, and you might need to look this up later. So we're always going to allow you to come back. Okay, so going over the benefits of interconnectivity, just to start us off. So this is going to be basically for databases in general. Like I said, we're going to start with databases and work our way up to blockchains. So data center interconnect, or DCI technologies, link two or more data centers with high-speed packets of optimal connectivity. A high-performance interconnection with the agility, blah, blah, blah. So let's go more specifically. Let's just look into this. So digital ecosystem density is basically how much you have there. So interconnected solutions link numerous discrete entities in different ways to form ecosystems or groups of ecosystems to facilitate data exchange. So it's basically like the more different groups you have, the more dense it's going to be, right? So it's just a way to determine how much you have kind of on the fly or very easily, even if you need to find out like more specifically to each group or whatever, or ecosystem. Proximity, so distance between things, so latency and things like that, your ping count and things like that. Those are all going to matter about proximity, how far away you are from other things or other ones or other connections. Direct connectivity, the DCI solutions offer direct connections that do not traverse the public internet. So there are some ways to do it publicly and there are ways to do it privately. And this website, they're specifically talking about the public version. And I think that's kind of important because the private version is just going to have more stuff on top. It's going to have more DRM and other things to help protect whoever's on the other side. Now, we also have global distributed exchange points. We're going to get a little bit more into this a little bit later. So keep that in your mind. There's such thing as a correlation of exchange points, and we can distribute that. So we actually do see that in blockchain, some blockchain technologies, normally right around like hybrid proof of work and proof of stake systems. But we'll get into that a bit more later with some mapping and stuff to show you visually how or why that is. So data sovereignty, a coalition provider of campuses in different countries. It's just data sovereignty. It's within things. There's might be sovereignty for data based on where it's origin from, or two, even though in the middle it might be going through a country where it might not have that sovereignty. So there are ways to keep that data sovereignty inside your transfers. And that's kind of important, but you don't have to do that. There are some companies that rely on the ability to move data sovereignty, even where you could like go from a district where it doesn't have data sovereignty, move it to a district that does, in order to give it data sovereignty, and then move it back where it doesn't with data sovereignty. So there are little tricks to this that might cause lag or other things depending on what you're trying to do. And with blockchains, some of that might be like if you're moving from blockchain A to B to A, or A to B to C, or any kind of multi-blockchain connection thing, you might see this issue more often. I just realized my thing's on top chat. I think it's a live chat. Yes. Alright. So when we continue going down, we're just going to see like the actual benefits from these things. So you can get global physical reach, you can get more comprehensive suites and infrastructures with connectivity services or connection services. So like you can do like, for example, they can tell you how many likes you have on the dang video. For example, that is an interconnectivity service. Proximity to cloud and SaaS platforms can basically get you stuff faster and more efficiently to ensure that your DNS is quicker loading or whatever, so you don't have to have as much lag in your downline. Nice. Worldwide locations, so that way, again, less lag and things like that. Scalability, this all is basically the same thing. When you come down to it, the last three things, exactly the same. And those last three things just give you better of the second thing, which is also the better of the first thing. Boom, done, roasted. All right, so that's all we really need from this site. But if you want to come here to read the rest of what's going on, I am in reader mode, so you're not seeing probably everything you could be seeing. Keep that in mind. There's more here for you to read if you want to look at this up later. But the biggest point here to get out of here is that the benefit of interconnectivity is simply speed, flexibility, robustness with your service, or allowing you to do more stuff with your service. That's really about it. And that's not bad. That's good. Awesome. Okay. Now we're going to go over why would an organization use like cross connections. So So this is kind of like really important. There's a lot of people there would be like, no, I don't need to do, you know, cross-server connection systems or cross-server communications, and there are tons of stuff that work without that. But there's a lot of stuff that can't work without it, and it's kind of important that you have some kind of ideal. But the part I really want to focus on is this: how to choose interconnectivity in a data center: speed, carrier, security, scale, and support. The five. Those are I keep wanting to call it the 5 S's, but carriers is not an S. The 5 S's of data connectivity: speed, carrier, security, support, and scaling. Again, I realize one of those is not actually an S. But the benefits of this cross connectivity always gives you like more on-site remote support, more carriers, more increased speed and reliability. You're going to be able to handle volume and distribute those bundles and have discount systems and have more things that most people are going to be worried about, especially when you're trying to run a business off of something like this. Okay, so all right. So far we're looking at basically definitions of these and also generic reasons why these are good things to have, why we need them. Because again, there's a lot of people that would say, well, we don't need this, especially in blockchain. You know, we got a blockchain, it's one blockchain, you should be able to do it all. Or I disagree, and that's why interconnectivity is kind of important. So some of the stuff that we kind of mentioned earlier is like those the internet exchange points, whatever. These are what we're going to be talking about right here. So PeeringDB is a database. It will allow you to actually find and get and distribute basically customers, your data, your service, your network, your everything, your internet. This is literally like moving internet people from one to another, normally to get them faster service. It might also allow you to get noticed, your network to get noticed, or something like that might help you get attention to yourself. So we're going to look a little bit more into what really PeeringDB is, because the more we look into it, the more it makes sense. And it's not much of a crawl, a very small thing. PeeringDB, as the name suggests, facilitates peering between networks and peering coordinators. So if you're a network operator, how does PeeringDB help you? It almost 1/3 of anonymous system numbers, or ASNs, register their interconnection data with PeeringDB. This means by using PeeringDB, you're adding your own interconnectivity data, and you'll be able to confidentially find information in networks looking to interconnect with you, where and how to connect with them as well, and they'll be able to find the same information about your network. Since the database is user maintained and validated by volunteers, you can trust the information is accurate and up to date. I disagree with that last part, but believe it or not, a lot of the ways that some of these volunteer systems work is they try to get it validated by people who don't agree with each other, to make sure that if they commonly fight or whatever in validations and they can agree on a validation, then it should be good. And that's actually kind of neat system to use in your network. So if you're an internet exchange point or XP, this data center facilitates and to help maintain the information in the database, increasing visibility and appealing to new existing customers. So if you're in the database, this makes it much easier for networks to find crucial information about your services and other networks. So like this is also a great way to like get your SSO more attention, even though it might suck. I know that's not a really great example, but that might be one that people will hear and understand from the how far off it actually is. So we're going to go into basically networks. We're going to be looking at actual networks. This is from researchgate.net. We've shown, I'm pretty sure we've shown this picture on the thing before, and this is basically an updated list. So from the last time we've shown it, so we have the A chain where one node can only talk to another node, and you got to work your way through it. Then you have a linear bus where everybody goes to the bus and then finds everybody. Then you have a tree where some things might be restricted to a single point, while other things are more accessible. A D where everybody can kind of see everything, but you still reliant on everybody to have access. A hub and spoke, which is one center centralized, and everyone has access to that center centralization in order to talk to each other. Fully connected mesh, which is basically like what we call distributed and decentralized, is that. Then partial mesh, the best way to describe a partial mesh is a DAG, or a directed, I don't remember all the words, it's a graph, it's a hash graph. And then multiple incomplete networks, which is like a tethered network, means they don't have to be a full network, and they can still communicate and talk to each other even though they have nothing to do with each other, seemingly. And then no connections, where they're just absolutely independent networks. Like that would be like Bitcoin versus Litecoin versus Ethereum, like Bitcoin versus Litecoin versus XMR. They all there. They don't really talk to each other. Now we could go that multiple incomplete networks is another one where it's like Bitcoin, Ethereum, Litecoin, XMR, where XMR and Bitcoin has that single connection point. Boom. But the whole point of networks is the ones we really want to look at: hub and spoke. Centrally connected chains like multi-chain networks is a hub and spoke. F, fully connected mesh. Most blockchains that are similar to Bitcoin, meaning like they just copy it off of Bitcoin, they're normally this. Bitcoin is a fully connected mesh. It is a decentralized and distributed network. Then you have G, which is a DAG, and then H, which is that multiple blockchains as a cluster. Also tethered blockchains or tethered networks is another one that would work with that. Also, atomic swapped networks would follow within some of these lines of H. Okay, now we're going to get into the actual, what we would call meat and potatoes of today. Right now, we've just been catching up. So today, we're going to get into the real stuff. We notice we're dropping down to just 3 now to keep it simple for you. Distributed, centralized, and decentralized. The architectures of a blockchain. So Bitcoin is a distributed, decentralized blockchain, or decentralized distributed blockchain. So a little of the first and a little of the last on here. Well, for example, BSC is a centralized chain, specifically a distributed, centralized chain. And DAGs tend to be more of a decentralized, centralized, but potentially partially distributed chains. It's kind of like a little bit of everything. And that's why it's that partial mesh in the previous image. In many ways, you can say one way to sort blockchains is to sort it in by its permissions plus distribution. So the two things added together. And that's actually a taste of what we will see in this image. For example, a distributed chain has even permissions. A centralized chain has pointed permissions. And a decentralized chain has weighted pointed permissions. So if you had to force each blockchain into a single point of these categories, for example, most proof of work chains like Bitcoin, Doge, and Litecoin are distributed in this casement. And while BSC and other authoritarian chains are centralized in this casement, then finally many proof of stake chains are going to be decentralized in this casement. Because that's, again, where we can only put them in one of these 3 cases, not a combination of. So, again, the last bit is only according to putting these into a single category based on this single image you're looking in front of you. Because most blockchains will be a combination of these depending on the situations and how you are using it. Because any of these 3 chains at any point in time can really fluctuate between any of them. Again, based on the actual chain and situations that you're stuck in with the chain, what you're doing, and also how you are actually using it, how you're accessing it, how you're talking to it, how you're communicating with it, how you're performing your actions. So these may not be the technical only 3 blockchain types, and we'll get into a full map later. But we can fit each blockchain into one of these 3, or all of these 3. And I think this is important to point out that, kind of like when teachers first told kids that the water and glass like water and gases are kind of tricky. Then later you find out about the superfluids and the supersolids and the solids that aren't really solid. And sure, you can fit everything down to one of these three states, like gas, liquid, or solid. But there are ranges of combinations of most matter sits in at any state time. So distributed is like a gas, and it will form shapes around to the least friction point amongst all points. Centralized is like a liquid where it can get around easy and find itself with, like when raindrops fuse together with larger bits. And decentralized is kind of like a solid where it has branches of strength that are partly reliant on its surrounding grains. But how wood and stone have mixed grains, there are natural flow that causes that rigidity and makes it quite strong. Kind of why like some people focus so much on decentralization and networking. Quite strong. All right, so hold on. I don't think I gave you guys this QR. This was from the engineeringprojects.com. Great site. Next, we're going to go back to ResearchGate because the network effect, normally I would show like a definition and be all nerdy with it, but today I want to show you this picture. Notice the blue node, okay? Let's call this the first layer in communication. These internal tips, as it's labeled, can be much of anything like a CPU inline for data, or it could be a miner that found a block, bottom of, like, if it's a miner that found a block, it'd be the bottom above the black dashes. So it'd be there's two bottom dots. The one on the top of the black dashes would be a miner that found a block. The competing miner that did not find a block, basically found a block but did not win, would be the one below those dashes. The node for the winning miner is just above the winning node dot, so the one in the middle with the arrow pointing to it. And then a listening node that witnessed the transaction or block finding, aka first witness node, that's the furthest top red dot. And if this was the CPU deadline example, the boundary tips would be the next layer on the chip, and then each layer after that will continue down until finding its way out. While this is the proof of work example, the boundary tips is actually like the very next edge of device hearing, the node activity. So the miner communicates, it found a block, to talking to two or other devices potentially, one being the owner or an operator, and another being a miner node or operator of some other operator, basically a non-owner operator. So then all the boxes in this section would potentially be nodes or operators propagating down until all of the network has a proof of this block being found, and all the data within it. So this network effect of propagation is considered a natural formation. And like how water is filtered by the dirt as it passes through it. Yes, we're going to be using water, gas, and solid references throughout this entire thing. It's just the natural way to describe networking. Okay. So we have this bizarre visual representation of a bridge action by Blaze.tech. And so A, or company A, sends to the bridge. The bridge communicates to the other bridge to have the second bridge send to B. So there are two bridges. Don't think of this like one giant bridge stretching over to the other, but instead think of it like a bridge that has a fleet of people in little stands that send telegraphs across a semi-dedicated line to the other side of the bridge for someone to get the message and then move it to B for you, or as you, depending on which chain you are. Hey, Bitcoin Live, awesome sauce on the screen. What up, what up? I'm gonna have to get the backdrop fixed. There's supposed to be a black backdrop. Glad to see you jump in, bro, Sue. So, I'm gonna show you a picture that, well, let me make sure you guys get this. Or I'm going to show you a picture of a real way to describe bridges. Okay, this is an AI image, of course, but as you can see, there's all these people here at the telegraph booth, and there's a city really far out into the distance. If you really look, there's an actual city. Like there's a guy over here by me underneath this clock. There's a city down there. That's where the other bridge is at. So this is communicating by telegraph to the other bridge because it's inter-server connectivity. One server literally has to talk to another server over the line in some way to actually facilitate a bridge communication. So we're gonna go right into the next one. And bro, so I know you're just coming in and everything, but I am using LibreWolf browser instead of Opera. And a lot of people don't realize this, but I've been using the original Opera browser. So I get the original Opera browser back when it was still by the Norwegian company. And then I upgraded all the way up to the current version with some crucial detail changes in the database. I'm no longer doing that because LibreWolf is supposed to be a lighter weight one, and we're doing some testing. And I kind of mentioned this in the beginning. I don't know if you were there, but anybody who comes back in, they came in now, they just heard it, so they know now too. All right, we're going on. So there's more than one way to do bridge. So this is the first example was called an open multi-network bridge. You have to have a bridge on both sides for it to work. Otherwise, it doesn't work like you'd like. Anything in, anything out. But now this type of bridge that we got in front of us is more like having a wallet on both sides that the bridge uses. So bridge A will put your funds into a wallet and lock it, while bridge B will now mint a brand new exact copy of your token sent, sometimes even mimicking the mint number. So what's the major difference between an open bridge and a locked bridge? Well, two things. Okay, first, the open bridge doesn't lock anything. So if someone knows how to communicate correctly to the bridge, either A or B, because they are not the same bridge, they could actually obtain sent tokens to that bridge that was sent for crossing. So bridge swiping is considered a type of liquidity rug pull, because that's what bridges kind of are being used for most times, cross-origin liquidity. So like trying to pull water out of thin air, sure, it works. You need the air, you need the water in the air in the first place, really. It's kind of like trying to pull, bridging is sometimes like trying to pull water out of dry air. You'll get something, but you are forcing it, and so sometimes it may not be tasty or great in the end. Bridges can be an expensive way to cross-origin pollinate, or to send someone from one network to another. While open bridges are cheap than locked, open bridges have more issues, with tokens just not appearing on the other side for a token return trip. Rosa, I'm glad you like this. So we're gonna jump in to the next one. This is again another bridge image. Now, so far you guys have seen a locked and an open bridge in super general contract. Now we're going to look at basically both halves of the bridge working simultaneously in this image, and we're going to be looking at a couple images here. So I don't think this article does a pretty good job at explaining what's really going on. Oh, actually, I have to correct myself. I misread that. I do think this article does a pretty good job at explaining what's going on. So if you want to read this later, here's the QR over there. Come back and watch. But right now, you can see two sides of the bridge, a white side and a yellow side. I'm going to zoom in, get rid of the QR. I'm going to zoom in. That's something I have not tested yet. Zoom in capabilities on this browser. Yeah, zoom in is not as good, but it does work. It's a little bit crisper than previously. I like that. So anyway, so the white side and the yellow side. Basically, the white side is the originating side, and or where it was sent, while the yellow side is the receiving side of where it's going. So we can see the red line incoming from the into the contract locks, and then it's minted on the other chain. So these are two bridges working as one in this example of lock and mint. So if we go down here, this really actually shows you what's actually going on. And this is why I love this website in this manner, because they do explain this more. Okay. they do explain it more. And I'm going to be pretty brief too. Information to the web app goes to the RPC, to the bridge smart contract, to lock the funds, to send to the other bridge with verification systems and hashes and other things, and a little bit of morphing sometimes, to then have that other bridge smart contract mint equivalent token to then be validated in the new chain for any multi-sig system to then be whatever, to then go to whomever it is to go to. Okay? This is actually quite a long process when you start looking down at what's actually going on. Everything in the bubbles, not because so like when we see this picture and the other picture, this is the actual on-chain stuff. Everything outside of this is not on-chain. Now let's go to the other picture. Everything outside the on-chain image you just saw is not on-chain. Web app, the input from you, the web app to the RPC is not on-chain. The RPC sent to the bridge, which is just a smart contract, is on-chain. It does on-chain work. Number 4 is technically off-chain because it's actually transferring information from one to the other. But nowadays, a lot of times, bridges are done on the exact same machine, so it'll have both bridges pre-designed or hub and spoke set up on bridges pre-designed, so that way 4 could be internal instead of external, but it still has to be sent to the other one, regardless if it's external or internal. It's off-chain. And then 3 is the next other chains, on-chain actions, smart contract, mint, validated, and then everything after that is off-chain. Goes back to the wallet, the multi-sig setup, and then the actual people seeing that they have what they have, or you seeing it got to them. Off-chain. I think that's really important to point out, because a lot of people think that a bridge is only this right here, and they forget there's other steps that can actually, like, you can go from web app to RPC and lose out just because the RPC sent it to the wrong smart contract. And that would be your fault because you inputted something wrong. And so, like, people don't, well, how is it so easy? Well, it's so easy as one of these on-chain things. Whoa. Okay, yeah, there is some, I gotta stop zooming in like that. There is some on-chain stuff. And there's some off-chain stuff that is easily the error. Easily the error. And that's the fear that people have with bridging. And it's a good fear, I guess, for good reasons, or at least. Alright, so as you guys notice, I don't have anything highlighted. I have not found a highlighter system that works without, like, just screwing me over on this one. And I did have to actually modify the Opera thing. Like, I had to put in, I believe it was an additional, like, it's like I had to hand install an extension to prevent my highlighter extension from sending to a server. And all the ones I have here, I haven't found a way to do that on LibreWolf yet, so I haven't found one that just doesn't do that. They all do that apparently. It's scary. Anyways. So, bridges still, because I think bridges is the one that there's so many different ways people have kind of tried to explain it. I have more than one perspective of bridges I have to squash. So this is the last one on bridges I have for you guys. We're going to simply show 2 workings as one and using an internet calculator to communicate between the 2 bridges and a simple how-to server communication. So if you see here, we have permission chain, public chain, we have a bridge. It's actually 2 different bridges with some kind of connection between them, either inter or outer connected. So if we go to bridges, which is why we're here, we have cross-chain, side-chain, federated, hash time locked contract or HTLCs, programmable token bridges, and trust minimal bridges. not all of these are the same. So a cross-chain bridge is basically all the ones I've been kind of talking about so far in the term bridge. Sidechain bridge is, remember when I said sometimes it's internal? Sidechain bridge can be an internal bridging of two, like a second layer or a sidechain, because sidechains are two chains that interconnect as one. They act as one, but they're not. And then federated bridges are basically kind of like a DNC method of connecting a bunch of random things that shouldn't be together. And it allows everybody to have their own method of permissions. Hash time lock contracts are something we will get into further because it is its own unique thing and should not actually be on this list at all. And then programmable token bridges is like that mint and lock USD thing we saw earlier, and trust minimal bridges is again kind of like its own thing, but still it's two at working as one. That's just one where they have, like, you have a blockchain in between the two bridges to communicate, to have a way to communicate data successfully without actually sending data. So you can have two bridges that can look at a blockchain to see when something has happened from the other bridge. So they don't even have to know the other one exists and be able to interact with them. So here is an image of, like, for example, a trustless bridge, or this trust minimalized bridge. So there's a lot of risks and things. More stuff here for you to learn later. I have done an entire episode on like tokens versus coins, because the big thing about bridges, they are best for tokens that are not native coins to the chain. So NFTs or chain-made tokens like meme coins. And if you want to watch more on that, this episode right here will help you get there. So now we're going to go into atomic swaps. So that HLTC, that's atomic swap. They're not actually bridges. People keep calling them bridges, and they're not bridges. This is one of the things I really wanted to squash. Because there were a lot of people that compare these two things together, and we're going to show you an image later of how they're vastly different, and the benefits and the goods and bads behind it, the pros and cons. So, alright, it says an atomic swap is an exchange of cryptocurrencies from separate blockchains. The ideal is to remove centralized intermediaries like exchanges and reduce the steps needed to actually trade tokens. But many exchanges and businesses have created swap solutions to make the process easier, and we're actually going to cover that later, the swap systems in comparison. We don't really care where the term comes from. It does mean changing the actual atomic state of the token or whatever, the UTXO. So key takeaways is an atomic swap is a cryptocurrency exchange between two parties that wish to exchange tokens from different blockchains. Atomic swaps are helpful that if you have only one cryptocurrency but need to use another one in a transaction, and you definitely don't want to go through like an exchange or something. Special wallets or exchange services are needed to conduct an atomic swap. Because the technique is still being developed and refined. And keep in mind, this article, I believe, is not that old. Okay? And only a few years old, maybe, the most. And it is still something that's actually being refined. Like, I remember people really talking about the ideal of atomic swaps back in like 2016. It was an ideal. And it didn't become like a reality, I think, until like 2019. Well, actually, I think we get into that later. It says then here that there's some information on that, so let's just get directly to that now. Atomic swaps rely on each party to provide proof through key encryption and acceptance of both parties through an encrypted key. So the history of atomic swaps. The concept was conceived shortly after altcoins.
currencies other than Bitcoin materialized. So the creation of altcoins meant some cryptocurrency owners became interested in moving capital between coins. We used to do it in something called pools. Okay, the first appearance was 2017. So people were talking about it in 2016, and then someone got it done between Decreed and Litecoin in 2017 for the very first time. Pretty cool. Because just the fact that you're able to do that means things. And specifically, we will get into atomic swaps. For example, if Alice wanted to trade 1 Bitcoin to an equal amount of Bob's Monero, smart contract would actually allow you to lock both amounts in respective blockchains. Once Alice agreed to trade, smart contract would then redeem it to those people on that network. That's really important. It's actually super important. Guess you just want that, and that's available here. Fast fact: a cryptographic hash function is an algorithm that converts data of variable length, such as a person's wallet address, and transaction information. It converts it to accessible nestable with a fixed length. In general, that number is generated and called a hash. An HTLC requires both parties to acknowledge the receipt of funds within a specified time frame. If one party fails to confirm the transaction within the time frame, the entire transaction is voided, and the funds are not transferred. You don't even lose, your funds are not even moved out of your wallet until it's accepted. This eliminates counterparty risk, or the risk that one party will actually be able to offer coins, decline, and still get the coins. You can't get rug pulled. Can't get rug pulled doing an atomic swap. That's the importance of atomic swaps. So, we want to really talk about how do atomic swaps work. Well, let's explain it differently. Atomic swaps use a hash time lock contract, HTLC, which acts like a virtual vault or cryptographic escrow account that keeps users' funds safe, only executes when the correct amount of tokens have actually been deposited to the contract. Each user must acknowledge the receipt of tokens within a specified and agree to unlock them. So, but if we read, it's set up in a way where, for the Bitcoin and Monero one specifically, it's set up in a way where you put it in the contract, but both people have to do the same thing in order for the contract to then even take your money. Nice. Alright, so they have more information on all of that. That's for you guys to have fun with later. I don't actually need to give you all this information right now. I think, is there more down? Is there something down here? There is something down here I need to point out though. The disadvantage of atomic swaps is DEX and centralized exchange remain in high demand compared to atomic swaps. So the disadvantage from atomic swaps is it may just be more difficult to get trades, especially high-end trades. They have a thing down here, atomic swaps versus bridges. While atomic swaps enable the peer-to-peer exchange of native assets, cross-chain bridges provide a connection between blockchains, kind of like that telegraph. Bridges can facilitate the transfer of wrapped assets via locking and unlocking or minting and burning mechanisms. To date, there's over been $2.6 billion worth, USD, lost in exploits from cross-chain bridge hacks, which is why the Web3 ecosystem is rapidly adopting the superior cross-chain solution, which they're claiming is by this Chainlink CCIP, which is just moving money into a centralized point before moving it onto another blockchain or something. We'll actually kind of show that later, how that works indirectly, but I won't mention it, so try to keep that in mind to find it. Alright. Well, I can't just go on and talk a little bit about this without giving you a little bit more about this. This is the Bitcoin Monero cross-chain atomic swap paper. This came out in 2020. So, the abstract. In blockchains where hash time lock contracts are possible, atomic swaps are already deployable. Yeah, you can already do it. But when one of the blockchains doesn't have this capability, it becomes a challenge. Monero. This protocol describes how to achieve atomic swaps between Bitcoin and Monero, 2 transactions per chain, without trusting any central authority, servers, nor the other swap participant. We propose a swap between 2 participants, one holding Bitcoin and one holding Monero, in which, when both follow the protocol, their funds are not at risk at any moment. The protocol does not require time locks on Monero's side, nor script capabilities. Does for the proofs to acknowledge of equal discrete logarithm across the Edward 52519 and the SECP256K1 groups within the ECDSA, at one time VES. Yes, those are all types of encryption methods and algorithms. As you see, logarithms is a bit less of an kind of like a lookup table. Okay, introduction. The last bit I'm going to read, so you know. We described a protocol for an on-chain atomic swap between Monero and Bitcoin. The protocol can be generalized for any cryptocurrency that fulfills the same requirements as Monero to any other cryptocurrency that also fulfills the requirements as Bitcoin. For an exhaustive list of prerequisites, see Chapter 3. Participants send funds to a specific address generated during the process of the lock, and each chain cross-chain, which each party can take control of the funds of chain swap automatically. Claiming of funds is either chain is mutually exclusive from the ability to claim funds from the other chain. During the process, participants do not expose their funds in the following protocol, accordingly, meaning with the swap is trustless and does not require any sort of collateral, allowing 2 strangers to trade without risks nor the help of a third party. It's really important. That's why this is the superior trade to all other ones, including that CCIP thing that they were trying to Cloudflare was trying to sell. Now, in case anybody out there watching this now or later, sorry, anybody want to take advantage of an atomic swap between Bitcoin and Monero? Here is a place that will actually help you get that done. They actually go through the steps, show you all the steps, go through the word. You got this, bro. I'm not gonna really go over it all. But we are going to say a few things. So the major difference between these two methods of bridges versus atomic swaps is when you bridge, you don't actually move the item to the chain. You're putting it in a wallet, either for an entity or a contract. Then you are entrusting that entity to push that object to the other chain and hope your object isn't already on that other chain. While atomic swaps actually moves the object over as much as possible in a way that is verifiable and trustless through cryptography. So far, if you are wanting to send a native chain coin to another chain, it's probably best to attempt atomic swapping before bridging. But if you're trying to send basically anything not native to the chain, like an NFT or token, then you probably need to go with a bridge. This is because an atomic swap is like moving an ice cube by turning it into a liquid to fall into a new location, while bridges makes an identical ice cube to place in the new location. So now there's 2 ice cubes. Whereas in atomic swaps, you have the same ice cube, it's just in a new form. Bridging is like making a copy and moving the copy. But what if there was another way? What if there was? So there is. Alright. Swapping is the next form of asset transferring from one database to another. So often in data handling, you will swap 2 variables, and that is an easy way to view this, but let's keep the state matter example. So if you have an ice cube you want to move, but you don't want to touch the ice cube, so you trap the air around it, heat it up and turn it, that air and heat up the air, then heat up the ice cube, turn it to a gas before cooling it down, then make it back into a new ice cube, and then be able to place it into its new location. Same water, new shape, but the same state in the end. So we are going to go over the images in the article, but the article isn't as bad, so I wanted you to at least have this article as a homework source for anyone needing more help with this topic specifically. We are going to go over some images in this article again, but here is the article for future reference. So after this is just the end. Nope. Yeah. Image number 1. Whoop. All right, so we are looking at an order book centralized exchange. Everybody deposits to the centralized exchange. Exchange does all the work. And then output. Done. Roasted. Boom. Sex is like going to an ice machine and only getting what's up front. But you deposit both money and liquid to get that ice cube. Rather, the next two options are more work input instead of money input plus your liquid. Let's get into them. So this is kind of like a self-checkout. And so a DEX is like picking your own ice cube someone left behind. Like someone else left the ice cube, so each ice cube is a different liquid maybe, and you just pick the one you want and then refill that spot with the liquid you have. It's almost like an even trade just about. And now swaps. So swapping is like moving the ice cube without touching by heating up or cooling down, captured by the air, blah blah blah, to another. Transfers it without transferring flavor. And here is more of a, like it's a Litecoin to Bitcoin swap, right? And I do think it's funny is, like just the simplicity versus the other ones we were looking at where there's a lot more steps to everything. It's just like in, out, boom, done, roasted. Everybody gets what they wanted. Okay. So here we're going to start kind of in the middle of the page. It's a decentral.tech article. So despite the innovative solutions provided by the Lightning Network, transitioning funds between Bitcoin blockchain on-chain and the Lightning Network off-chain presents new hurdles. This is where Bitcoin submarine swaps come into play. Now, we are going basically over submarining because now it does exist in more places than just Bitcoin. But it's always been something available in Bitcoin. It's how you can actually have paper Bitcoin. It's just now there's a lot more ways to do it. Submarine swaps are actually a novel mechanism that allows users to seamlessly transfer funds between on-chain and off-chain environments without needing to close or open payment channels. This is achieved through the use of hash time lock contracts, and this is specifically when they're talking about Lightning Network submarining. Because if you submarine to a paper wallet, well, it's not quite the same, and no one, it's not done in the same way. That's all I'm gonna say. So this one is what you're seeing here on the site specifically for like second layer solutions off chain, running localized off chain, not running paper off chain, but submarine. That is why we were able to do submarining, simply because of paper. Paper off chain has always been available. And it says here, I do believe there's a way to reverse submarine chain off chain to on chain. It says on-chain transactions occur directly on the blockchain, on the Bitcoin blockchain. Each transaction is verified by network participants, known as miners, and then added to the network. Okay. So it no different than the actual stuff. So to address these challenges, off-chain transactions were introduced as a solution. Off-chain transactions occur outside the Bitcoin blockchain as a second layer, such as the Lightning Network. These transactions do not require the immediate individual verification of a blockchain, allowing for instant transfers with minimal or no fees. The Lightning Network, for example, enables users to open payment channels between each other, blah, 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 blah. That's kind of like an ad. The distinction between on-chain and off-chain transactions highlights the innovation approaches being developed to overcome Bitcoin scalability and transaction fee challenges. While on-chain transaction provides the security and decentralization that's fundamental to Bitcoin. Off-chain transactions offer scalability and efficiency necessary for currency to function as a practical, everyday payment solution, but it is not the same. Submarine swaps plays a crucial role in this being capable. Alright, so we don't care that. Lightning Network right now, we've talked about it before and stuff. If you want to check out those, go view them. Make sure you have R. So, this beautiful little paper right here. Basically, what I am showing you is a paper over merge mining. Mostly because I know what I'm about to explain is happening. I just don't know what it's being called. But we are going to talk about merge swapping. And if there's anything to be learned from this, is that merge mining and asset merging are using similar principles. The hash can be used twice, so to speak. So this is the big point of merge mining, that any hash could be good on another chain. The hash is set up enough or similar enough to be so. So merge swapping is like sending two assets to obtain one in return. You may send multiple tokens to get a single NFT, or you may submit two tokens to merge into a new one. This is what is called in different this process of merging two to get something different output. So you send two assets to get one in return, like multiple NFTs or multiple tokens to get one back. This has a different name in a bunch of different chains. For example, on the WaxP chain, it is called merge tokens and liquidity tokens. So, and also like tokenized assets. So when you send two NFTs to get like actual tokens back, not NFTs back, that's a tokenized asset. And then you can send those tokens to get NFT in return. And it can be multiples of multiples to get multiples of multiples. Liquidity tokens is the one we take two sets of different tokens, merge them into one new output token, and anyone who interacts with that one output token with any one of the two tokens that was used to make it will get a return of the other token equal to how it's set up. And as we see here in the actual image, it's talking about how it's just basically using the data from one to a different one, and it's setting it up in a manner that works and allows it to be validatable, and that's really it. So boom. But this actually goes further into how the inner workings work and how different things work. I think this is just kind of an important part where you kind of just see like the data is just being reused elsewhere. That's kind of important, because when you look at it just simply like that, it's going to be easier to keep going on with what we're talking about. So this is how token system works loosely. I couldn't find an actual site with a real asset merging definition that wasn't actually talking about EP61 merger, which is just a change of proof type, or basically talking about company mergers. So this image shows what a merge asset kind of looks like. The Uniswap pool token, represented as an order book NFT in this case, contains enough data to be able to explain to the liquidity provider how much of what is worth of what for exchange. Some merged assets may be using NFT proof on two chains to allow for seemingly native bridging between two chains, which is reverse merged asset, but technically the same process, just that backwards, and we'll kind of get a little bit more into that somewhere else. We'll have an example of that somewhere else, I believe. So, yeah, we'll have an example of that somewhere else. I'm not going to get into that too much now, but it just shows you that basically we have two different tokens interacting with one token equally for simultaneous type of output, or autonomous types of output. Yeah. Okay. So here is an image of state matter. Maybe you remember this from school or something. This is in a high resolution. Here is in the same high resolution, the same matter state, but for blockchain style databasing specifically.
let's look into this a little bit, because I already know this is why some of you are here today. So if we, let's go back. If we go back and forth, matter is in the middle, so hard matter. Then we have liquids above it, gases to the left, solids to the right, plasma down to the left, and then bone and state coordinates down to the right. So here, distributed, decentralized, permissionless ledger is in the middle. It's a single. There's a 1, so it's a single object. That 1, and then to the left we have distributed ledger, also a 1. That's like a gas. What is a liquid? Centralized or authoritarian or permissioned ledger. There's the 3 forms of ledgers that are basically all the same. Just different ways to say it. And then the solid is a decentralized ledger, which is a 1. The DAG ledger is a plasma in this sense, and disjointed or offline or paper ledger is the bone and state coordinates. And that's again 3, which all basically mean the same thing, or can be the same thing in retrospect. Okay, so to get from like any of these, we have these lines, and it shows you what you either have to add, remove, do. You go from one to the other. So we're going to start in the middle. Starting with a decentralized or distributed decentralized permissionless ledger, you can add permissions to go to authoritarian ledgers. In authoritarian ledgers, you remove permissions and add decentralization to get to the other one. So permissioned ledgers or authoritarian ledgers, they can be distributed. They're not normally decentralized. Can be, but they're not normally. The big difference is permission layers. It's pretty much the only difference. So going from a distributed decentralized permission ledger to distributed ledger is, as you're seeing here, you remove decentralization to get there to distributed, or you add decentralization into distributed to get to distributed decentralized. They both pretty much can be permissionless. They don't have to be, they can be. So then going from this distributed decentralized permissionless ledger to decentralized ledger, you're removing distribution. Okay? Or you're adding distribution. So a decentralized ledger and a distributed ledger can be the exact same type of ledgers, just how they get out there is different. That's the best way to look at it. How they get out there is different. How they network connect is technically different. Okay, and you can see there are round ways to get to everything, from everything pretty much. If we go down to the plasma side, removing rigidness and adding multi-ledger permissions gives you a DAG ledger. Going from DAG to decentralized to the DDPL is like, or a basic Bitcoin, is you reduce to a single ledger by adding rigidness and removing some permissions. If you wanted to go DAG to disjointed, you have separated confirmations to verifications, and same thing, to go from disjointed to DAG, you need to have separated confirmations to verifications. So keep in mind, DAG normally has separated confirmation and verifications, but it doesn't have to. While disjointed is only reason why you can have like paper ledger or an offline ledger or a disjointed ledger is because it has separated confirmations to verifications. Those are separated. And you're gonna see, even going from like the basic Bitcoin ledger to the offline ledger, it's you need a submarine with separated confirmation of verification. And that's the whole reason why that one site was saying it's like that hash time lock contract thing is like the way to go submarine, to submarine a transaction. It is separating confirmation and verification. So now we can get to any of these by doing little changes, but we want to look at the further outputs. Like if we go back into here, we can see solids have more things it's reaching out to, gases have more things it's reaching out to. What are the other things these databases are actually reaching out to? So for example, a decentralized ledger, a basic Bitcoin ledger, a disjointed ledger, or a DAG ledger can all
have some form of IPFS styling or databasing. If they add, remove, do some changes and tweaking, they can get to a point where they're similar to IPFS. So, is IPFS a blockchain database? Kinda, right? Even torrents are kind of like blockchain-based databases. So if we go up to this other point, we can see there's a controlled point databasing at the very top corner, at the top right. So we can have something that's very centralized but very controlled for the entry and exit points. And that's kind of important. This controlled point databasing is when you control the entry and exit, not everything inside of it. Then if you go straight up, you have full authoritarian databasing, where everything has to be allowed. There are no actual allowances. And you can automate all that, but there are no actual allowances. And then in the top left, you have no point controlled databasing. So it's basically like controlled point databasing, but instead of the entry and exit points being controlled, it's everything else that's being controlled. So for example, like for authoritarian databasing, I would say it's like BSC, right? I would say something like the BitcoinLivejn network is more like a controlled point databasing. And then a Ripple is like the Ripple network or whatever, or the RPXL, XRPL or whatever, is a no point controlled databasing where the entry exit isn't really controlled. It's more like everything inside of it's more controlled. So now if we go all the way to the left only, we'll have user or semi-controlled databasing. So user controlled or semi-controlled databasing. So still, control is still being used even on the far left side. So I want to go all the way back to the far right side to show you what was on the far right side that we kind of skipped over. It was dynamic directed databasing. So now the control is predetermined, basically. Predetermined controlled databasing. There's still control on the right, it's just predetermined, which makes it dynamic. Now we'll go back to the far left bottom. We have tethered database. This is allowing timing drift, or basically things to work fractured in groups. A lot of times graphing technology is used with tethered databasing, but tethered doesn't mean fully fractured. We go all the way down to the bottom, off-center to the, straight down the bottom, not off-center, straight down the bottom. It's just completely fractured databasing, 100% fractured databasing. Like IoT databasing and stuff like that is normally tethered. But there is a way to have fully fractured databasing, which traditional torrents are fully fractured databases. And then we get back to IPFS. And so there is some amount of control, permissions, blah, 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 throughout all of these types of databasing. But how much of what each one has is dramatically different between them all. And that's kind of why some of this is difficult for people to explain. You can have 5 ways to look at distributed centralized permissions ledgers. Well, of course, there's like 5 different connections to it, man. Of course, you can have 5 different ways to look at it. All right, so let's go into a more simplified resolution. Let's go into a lower resolution. So this is the same kind of mapping, just a lower resolution. And now let's go into the blockchain version of it. This is the blockchain version of it, so pretty simple. The whole point is going to simplify the differences between these things. So if we look at the very bottom, decentralized, right? That's a solid, right? I think. Oh, yeah. Dependent. So to go from decentralized to plasma, you have to be less dependent on time mechanics. To go from plasma or fractured to decentralized, you need to be dependent on peer-to-peer timing or block time or hash time mechanics. Like Bitcoin, for example, uses hash time mechanics, and there is such thing as peer-to-peer time mechanics. A lot of times proof of stakes use peer-to-peer time mechanics in with block time mechanics, which I just now realize I misspelled block. All right. Going from decentralized to centralized, you need to be dependent on control mechanisms. Go from centralized to decentralized, you need to be less dependent on control mechanisms. No one said that there was no control mechanisms in decentralized. It's just you're a lot less dependent on it. While centralized, you were completely dependent. And again, it's going to be the exact same thing to go from centralized to distributed. So what's the difference between distributed and decentralized? Well, from we go from decentralized to distributed, you have to be less dependent on distance-based mechanics. And distributed to decentralized, you need to be dependent on distance-based mechanics. So a distributed decentralized system can be and is not required or dependent on time-based mechanics that are distant or non-distant related. Kind of explains the flexibility of Bitcoin, right? So to go from distributed to plasma or frag is also fractured in this case. It's less dependent on time mechanics. And to go from frag or fractured, you've got to be a little bit more dependent on those time mechanics. So frag is basically like the distributed and or decentralized, except for the fact that it's less, it doesn't really about time mechanics at all. Like, they super literally don't matter. They're not involved with verifications or double checks or anything like that. I mean, to be honest, in some reality there is, so don't take that like gospel. It's just in relation to how distributed and decentralized are reliant on time mechanics. Frag isn't related in that same way, where you could verify things that are completely far off sketch, just because of DAG has the ability where it's like, yeah, we might not be in sync anyway, so we have to be in that consideration. Alright, so here is the one image I think a lot of people are going to be here for. This is going to show you the main differences between bridges, swaps, DEX, liquidity merging, DEX, almost all of them. So if it's not reverse merging or atomic swaps, it's this very top bar. Okay? If it is atomic swaps, it's that middle bar. And if it's reverse merging, it's that bottom bar. Let's explain this. So this top bar, we have blockchain A and blockchain B. So A on the left, B on the right. So we're looking at blockchain A right now. Bridges, swaps, SEX, DEX, liquidity merging. Person A or entity A interacts with blockchain A. There is a token on blockchain A, and you see now the actual action, bridging or swapping, whatever, that causes this orange thing is the action. The orange little jump, that's the action. These two, there are now two tokens that are identical that exist. Only one should be usable at any time. Doesn't mean that's the only way it goes though. So now on blockchain B, again, only one should be usable at any time. There's a brand new token of the basically a copy of the other token now on blockchain B, which then goes to person B. So this little black line in the middle is the algorithm or contract or bridge or the thing that is the thing we're talking about. Well, almost all of these, it's going to be some form of smart contract. And that can also be an algorithm. So, nice. Going to atomic swaps, though. So, blockchain A, entity A, interacts with blockchain A, performs an atomic swap. See how before it was an arrow to an asset, and then an asset arrow to a person. Now it's morphing. The arrow and the asset is morphing. The token is transmuted. Transmuted tokenism. There's no new supply. No duplicate tokens to worry about. And this is being done by having a contract that requires the trustless method to lock in release. There's no minting involved. There's no making or redistributing or having more of. It's nothing new. Like the top one, you're literally creating a new token to mimic the first one, creating a duplicate. It looks exactly the same, identical. I don't want to use the word duplicate. They were identical. Now there are two. There was one, now there are two. Okay? That's a huge difference. That very first one, there was one, now there are two. The second one, atomic swaps. There is no new amount of any one of these tokens. What was before is now the same, but in new hands. No, not a new token. Maybe a new UTXO. And then interaction to blockchain B goes to B. Very smooth. Now this bottom one is reverse merging. This is basically happening at the exact same time. So this is kind of confusing. But imagine A and B, like blockchain A, the left side, and blockchain B, the right side, are going to be happening simultaneously. Entity A interacts with the blockchain, either A or B, and two new, brand new tokens are being made at the exact same time, which are exact duplicates of each other. How many of these should be usable at any one point in time is dependent on the contract. For example, there's a way to do this on Wax Key, where all of the copies are usable at the exact same time, even if there's an infinite number of duplicates. So, you could also have it set up to where only one can be set up to be used at any point in time, even if, again, if there's an infinite number of duplicates. All about the contract and how the contract allows the transactions amongst each chain. And that's kind of important. So reverse merging, you need the contract that you're reverse merging with to have the same contract on all the chains in order for it to really work. And you're doing it all at the same time, so at once you're minting all the tokens that are going to exist. While the very, very top one, you might mint a token and then someone else might create a copy of it on another blockchain that you weren't aware of, or asked for, or had permission, or got profit of, or anything. It no longer matters. It's out of your hands. That went to the public. And that's the drastic difference between these three. One is simultaneous and you have control. One has no difference between A and B. It's just moving it literally from person to person in a trustless way. And the top one is actually creating new by someone else. Someone else. Alright, so if you wanted to snag any of the images from today's episode, you can actually visit today's episode folder from the GitHub right here. You can see there, right there in front of you. And we are in the 3D Changes GitHub. I can give you that one too. So, alright, so how our database really connects is quite important, don't you think? I think now, if anything, you're probably realizing more important than you realized in the first place, because most people probably didn't really think it had much of a difference. But now you're realizing how it connects could be the difference between having, like, getting unregistered duplicates of something you made, right? Or knowing about it and having control over it, or no new duplicates whatsoever. So how our database connect to each other and to themselves becomes more important as it's a blockchain, when the data container blocks in this case are almost always directed. How the different ways these databases are directed is really what we are identifying. We show that there is only one blockchain connection method that can transfer assets from one chain to another, which is atomic swaps. Then the only other different method is reverse merging, which is when originating of the asset chooses to push the asset to multiple chains, normally simultaneously, while the other methods, all the other methods, are simply making a copy of the asset onto another chain. And oftentimes when this can be done against permission of the maker or originator, or even the originator contract. Say for example, the originator contract has permissions set, and you can actually use a bridge to get away from those permissions if the originator contract isn't on the chain that you're bridging to. So there's actually ways to get away things that are not allowed. Like you can actually buy a token, bridge it to another chain, and then offshoot it before it's allowed to be offshot. Like, for example, if it has some form of lock mechanism or something. And maybe that lock mechanism doesn't work right on another chain, and that's how you can, lock it and send it at the same time. Which would mean it would be locked on one chain, sent to the other chain, you can lock it on that chain, you go back to the first chain, and you'd be probably wouldn't actually lock it for a second. They'd probably just send it, still have it, or you unlock it, then take out the fee. You get a fee hit to you don't care about, because you're gonna get something back while you still have the full amount locked somewhere else. It's one of the reasons why locking tokens is kind of risky sometimes when you have multi-bridgeable token systems that exist nowadays, like with ETH to Sol and things like that. Okay, back to where we were. All right. Okay, so next time you think you are using wrapped Bitcoin on a non-Bitcoin chain, unless it's been ported or submarined off-chain from the original, or it's been morphed into other native tokens like an atomic swap, then you are using a falsity. It is just a token. This does mean that very few chains actually have true interoperability. This because when you are minting multiple assets on the different token chains, that's not working together. That's not even sharing information. That's just simply copying and pasting from one chain to another. That's like downloading something off the internet. The original still exists. Only atomic swapping, even if submarine into a forced atomic swap, as long as it can be verified on the other chain and the originating UTXO isn't being used as if it was never sent somewhere else, then it is the only way to move any asset to any other chain natively. And in any case, that isn't a native coin to a native coin will require extra work. I'm sorry. Atomic swaps can only do native coins. Non-native coins require extra work, and for most points, it just hasn't been capable as of yet. I mean, it's technically possible now with NFTs on both Bitcoin and Stacks, and Bitcoin and Monero. And again, we've also had NFTs on Monero as far back as I want to say 2017 when Cities of Download, but I don't actually remember when Cities of Download got started publicly. I just remember when it got started in the background. But yeah, that is today's episode. It is a chunky, thirsty bit of an episode to have to go through. There's a lot of technical work, and I am aware, and I don't really apologize. I'm trying to break it down as simply and as easily as possible, because, I mean, that's what I'm here for, right? I'm going to go ahead and do the exits, the outs, and I will see you guys next time when we talk about what it is we talk about.
Yo, did you think you know? Did you think you hold? Did you think something new? That's the goal, a seat from a new degree, and get the change your mind needs to find something new. Wait, really easy for many, but when a wall appears, sometimes up is all you see. So let's 3D guide to the side, yo, where there's a door, no. Just be careful on your way up, for the first step isn't don't say no. A little bit later, with something different. But regardless, so maybe perhaps it was that missing piece you was needing. Maybe it was that simple message you was searching. Definitely it's just differently in time for D. Fraying our mental mental mind state. Separate mind while I'm on makes a bang. Boom goes the blast of thought. Boom goes the last spark with blood. Boom, boom, the mental mind tank. Don't let your perspective hit you on the way out. Don't let your perfect you. Don't let it stop you when you're down. Don't let the dire things stop you from getting excited. So the photons are delighted. Don't hesitate, step weak, keep your mind up the hash rate. Let me surrender.